Okay. So now we're going to shift gears. Now this case is going to be more about optimization. So when you are trying to develop a project in a market, there are a lot of different variables associated with that and a lot of decision making that needs to happen. So you have market dynamics, the signals, the way the batteries are going to be dispatched in the market is going to vary from market to market and market rules. Obviously, the location is going to have an impact on your auxiliary consumptions. And then if you are trying to optimize your return on the project, you are looking for favorable or optimized augmentation strategies. So you probably want to build less upfront and then trying to come back and add capacity at different years so that you can maximize your return. So all these questions, if you are trying to make more firm decision, that needs to be informed by more detailed and accurate simulation. So this case study here, we're going to try to run through some of these design parameters that can impact your basically decision making. So the example we have on hand is a similar 100 megawatt for our project, but now it's going to be market specific. Previous one, it was just one cycle a day. Now we're going to be focusing on an ERCOT North market. So we'll see how can we generate a market signal and then utilize that to do our design. 20 years, deployment strategy is going to be augmentation. So that's different than the last case. It was a 10-year overbuild. Now we'll try to come up with an optimized augmentation strategy. Obviously, location ERCOT North, the battery and inverter will keep the same. And if you jump to the software interface, let's start a new file and give it a name. We'll go ahead and then save this file. All right. So once we have saved it, we'll come here under general. We are going to define the power and energy requirement. So 100 megawatt, 400 megawatt hour, 20-year project life. Under deployment strategy, we will select now augmentation. And you'll see as soon as we select augmentation, these two tabs here, augmentation and financial, both become enabled. Because augmentation, when you're going to do that, and we will use our Augmentation Optimizer feature, that is also going to use the financial parameters. And I'm going to cover that more detail. So you select that, then you come to the auxiliary load source. You can choose whether to do it from separate source or POI. Previous example was a separate source. This example, we're going to do with POI. And that basically means that your battery is going to be supplying the auxiliaries. So obviously that's going to result into some more throughput coming from the battery. And you'll see the impact of that on the degradation as well. Eventually, you select the transmission type project. So that brings us the GSU. So select T-type under interconnection. And then under simulation option, we're going to select all the three options that are available there. First option, financial results. We will look at that because we want to optimize the project return. Reduce battery degradation. Big part of it is based on how the battery is going to degrade. So we're going to enable that. And the last one is the reduced enclosure temperature regulated aux load. A big portion of the auxiliary consumption for battery sites really is being consumed by the heating and cooling. And that depends heavily on the ambient temperature, the C rate, and enclosure design. So when you enable this option, that allows you to get that variable temperature auxiliary consumption that varies with these parameters. Once you have done that, you go ahead to the interval data. And previous example, we used standard cycle. This example, we're going to use the time series. When you select the time series option, what the program is expecting it to input is a charging discharging pattern in terms of power profile. And this is where we can use the generate from market signal feature that we have in the platform. So if you click here, we are targeting ERCOT market. So you can come here, you can input the power capacity you want to commit to the market. So in this case, we're going to commit the full capacity, which is 100 megawatt. And the duration is, there are 1 to 6 hour duration that you can choose from. So we are focusing on 4 hour for now, this example. You select 4 hour. And then if you can select this drop down, if you select the drop down, you will see that all the 4 hour market signal that are available. So right now the platform support all 78 areas in North America, so New England. So all the major markets are here, and that includes market in Canada as well. So in this case, you can go ahead and select ERCOT North signals, this one, because that's the market we're targeting. Once you select that, then you also have the option which year you're going to take as your design basis, because we provide up until 10 years in future the forecast of the market. So you can choose whether you're going to use 2026 for your basis, or if your project placed in service is 2029, let's say, you can choose that as well. So I think, for example, this one we just is 2026. Once that is done, you will go ahead and give the file a name. And then you'll go ahead and click Generate POI Profile. So what it does is, you might have noticed that as soon as you click this, it populated this field here. See that in the CSV file? That ERCOT North 2026, that's the CSV file we just created. So it basically generates that CSV file and it populates it here. And then if you go under diagrams on the right-hand side here and go under POI profile, under POI diagrams, you will be able to see how that profile looks like for it. Okay. And then this is a power profile. So negative basically means charging, positive means discharging. Now, some of the folks might have questioned, I mentioned North American market. So if you are in a different market like UK or Europe, how are you gonna input your own signal? So one of the thing to note here is this feature, yes, it does support North American market now, but you can also bring in your own signal. So if you are in a UK market, you can get the historical data for that market and you can import it to this option, because this is a CSV file format. So any data that you have, if you organize that into the CSV file format and add it into Storlytics user files folder, you will be able to select that and use that as your design basis. Then we move to the TMI data option. One of the critical information input is that a lot of the performance depends on the location of the project and ambient condition. So the way you tell that to the program is through the TMI3 profile. So this is a typical meteorological data profile. So it has ambient temperature condition. So we're going to go ahead and select Texas. And typically, even if you are outside the US or North America, if you go to the NREL NSDRB website, you will be able to give the your location and download the TMI3 file for your location for free. And you can download the file and you can add it into the Storlytics user folder, and you will be able to select it if you are in other part of the world. So we did interval data. So once that's done, you move to the equipment. So under equipment, you have two options, two ways you can input your equipment information. You have standalone models or integrated models. So for standalone model, you have to tell which battery models, which inverter model, and which enclosure model you're planning to use for this simulation. And if you select the integrated model, so in that scenario, it's more of a integrated product that you will be selecting. So you can go ahead and select a Sungrow or a Tesla or other integrated products. If you select that, for example, in that case, you will see that based on that model, the standalone, the battery and inverter enclosure is going to be automatically populated. For this example, I'm just going to use the standalone model option. So we're going to use standalone for the battery so that everybody can run it. We are going to use a generic model. So you see this one, so generic LFP 280 ampere hour. Inverter models, we will use the SMA SCS 3950. And then Enclosure also, we're going to use the generic model so that everybody can follow along. So once you have selected the equipment, so you have done the general interval equipment, next important thing that you have to input is your financial model. So you will jump to the financial model parameter. You will come here, and this is where you have to input the financial model that you want to be used by your augmentation. If you click this green button here, that gives you access to the financial model editor. So in that way, you can go in there, review the parameters, and basically update them and save it as your own file. I'll go ahead and walk you through some of the parameters that are in here. So the financial model initially starts with, there are some generic parameters around your financial model. So you will have your discount rate, and that's important because a lot of the calculation the Augmentation Optimizer does, it looks at the net present value of your overall cost of ownership. So everything is normalized with respect to present value. So you input your assumption on discount rate there. If your project is eligible for ITC, you can input it here, your ITC percentage. You can also define at what year you want your ITC to be applied, because a lot of times your ITC doesn't get applied immediately at year one. Depends on when you basically file it. So you can do it at year 2 and 3 as well. You also can choose what percentage of your CapEx is ITC eligible. So if there are certain portion that is not eligible for ITC, you can control that through this parameter. You can also select your depreciation. So you can select your Makers 5 method, or you can do bonus 100. If you do Makers 5, you have the default schedule, but if you want to give any custom schedule based on your country or location where you are at, you can go ahead and update the CSV file, and that will allow you to input your own depreciation schedule. You can also input your corporate tax rate, because that allows you to calculate your savings because of the depreciation. And also you can control, typically there is a 50% reduction factor. If your project is ITC eligible, your depreciation basis is reduced by 50%, at least here in the US. So you can control this parameter based on your project specs. Once you have done setting up all this, then you can go ahead to the cost parameter. So the cost is divided into 4 main categories. Sheikh covered it quite a bit, but I'll just go over them briefly. On the equipment cost, you basically input your battery dollar per kWh, any future rate that you are predicting the battery price is going to go down. And especially for augmentation, this is an important parameter, because that declining cost of batteries are going to have an impact when the Augmentation Optimizer is going to tell you to add batteries. So if you have 3% versus 5% versus 1%, you will see that augmentation schedule is going to vary based on that. Similar to your power electronics cost, as well as your change rate, your GSU cost in dollar per kW, and also high voltage breaker cost you can input. Then you go to their Opex, because we look at the overall total cost of ownership. So you also have to input some of the Opex information. So standard warranties, SOH guarantees in dollar per kWh basis. A lot of times there is going to be escalation in your maintenance contract. So you can input those escalation percentages. Also, there is going to be a rate for your auxiliary energy losses. Obviously, these systems are not 100% efficient. So you will need to pay for those energy losses. So you can set the rate for your energy loss, and also
Jakir, so this parameter was asking about this parameter, if they can edit that. So how much for your benefit, this is where you can edit the rate of applied, or the tariff applied for energy losses, not just the rate itself, but also the rate of change of that rate in the next parameter. You can assume that, okay, every year for maybe energy's getting more expensive. So in this case, we're assuming 2% increase in yearly cost of energy here.
Yeah. So you have your auxiliaries, and then you have a separate loss for basically your system losses, transformers, balance of plant, and others. typically, if you set it to be fed from POI, it's going to apply same rate for system loss and auxiliaries both. But if your auxiliary is being fed from a separate source and you have a different rate for your auxiliaries and a different rate for your system losses, you can actually divide them up and set different rates for them. So that option is also available. Then you go to the augmentation cost. Of course, when you are doing augmentation, there are some costs associated with that. There are some fixed costs like plant integration, project management, and controls integration and others. So you can input them, and you can also input that because labor is getting more expensive with time, you can also input the percentage that those are going to be escalating. And then there is also some part which are basically it depends on how much capacity you're adding, right? So maybe adding 5 inverter versus 10 inverter and 5 battery block versus 10 battery block. So you have to do foundations, civil works, and others. So those are your capacity dependent parameter that you can update, and that's taken into account in the backend. And last but not the least, we have the balance of plant. So this is where a big portion of your overall project finance is also the EPC cost. So this is where you can input your interconnection cost, fixed cost, variable cost, your EPC engineering cost for electrical, civil, actual electrical work and civil work, project management, commissioning, any kind of fees. Pretty much all the details typically you need can be added here, as well as owner's cost. So that covers us on the cost side of the equation, and then we jump to the revenue side. So on the revenue side, since we are in the topic for Augmentation Optimizer, we mostly focus on the cost because Augmentation Optimizer is trying to get you to meet your technical requirements at the least cost possible. So cost is the most important for the Augmentation Optimizer that we'll be running. But the revenue is also important when we are going to calculate the IRR parameters. So I'm just going to walk you through the revenue options that you have. All right, so we are talking about the revenue. So revenue, we have two structures, tolling agreement and merchant market. So tolling basically is your typical PPA structure. If you are doing a fixed capacity tolling, you can set that in dollar per kW month. Typically with your tolling agreement, there is going to be some performance matrices associated with that. And those are typically, you have to maintain a capacity, you have to meet a certain RTE, and you typically have to be available at a certain amount of time. Otherwise, there is going to be some LDs associated with that. So you can set those LD parameters as well. So in that way, you can determine if your project is underperforming, how much hit you're going to take on the revenue side. And then there is also merchant market option. So in the market option, you basically make money depending on how the market rates are and how we are dispatching the battery in the market. So I think Mohammed Shihab also had a question about, can you do merchant market ancillary as well as capacity together? So yes, you can. So the way it works in the first part, market services, this is a CSV file. So you see that it is inputting the pricing from your market. So you can actually input that into CSV format from your market. And if you expect that those rates is going to be changing year over year, you can input that here as well to the rate adjustment factor. So that's based on market merchant services. Now, if you want to stack a capacity service, maybe like a PJM, you can do that to the capacity payment. So you can come here, you can select some of the parameters like ELCC, penalty factors for capacity payment, what is the clearing price for the capacity market in dollar per megawatt day, if those are going to be changing. And typically these contracts will also have an annual penalty cap. So you can set that as a factor as well. All right, so I think I covered the financial model in detail. So practically taking us back to our original question is we want to design the project and get the augmentation schedule. So once we have inputted the cost, we're going to go back to the augmentation tab and we will utilize the augmentation optimizer option. So there are two options here. You can bring in your own augmentation schedule if you have one, and the program will help you to show you the results based on your augmentation schedule. And then this augmentation optimizer option is where Storlytics optimize the augmentation schedule for you and define it for you. If you select that option, you go under augmentation optimizer, you have to select whether you want to do an AC augmentation or DC augmentation. It also depends on the type of product you have selected. Based on that, you can select AC or DC. And then there are three parameters that you can choose whether you want to define to make the optimization search more restrictive, or you want to make it more broader and let the program choose it. So for each of the parameters, you will see that there is a user-defined option and a Storlytics optimized option. So if you select Storlytics optimized option, then you don't have to input anything. The program is going to run thousands of scenarios in the backend and then going to give you an optimal schedule. But a lot of times, teams might have preference that I do want my initial overbuild to be 3 years. I'm not going to take anything less than that. So in those scenarios, you can actually come and define that parameter yourself. All right. So once you selected these inputs, you then can go ahead and click the Run Augmentation Optimizer, and in a message box will pop up telling you that this will need some time because it's running a lot of scenarios in the backend. And if you click yes, the Augmentation Optimizer will start running. Now, depending on your machine speed and the amount of options that you have given here, it might take some time. But after you have done running, it is basically gonna generate an augmentation schedule and populate that here in the second field called the augmentation schedule. So you will see after successfully running the Augmentation Optimizer, a augmentation schedule is being populated here. So I'll skip running it now for us to save time. I have already pre-ran it. So if you go to under File and Open and go to Open, you should see there is a project file name example ERCOT BESS _AC. Click on that one. Yeah. So that one I ran pre-built, and when we ran the Augmentation Optimizer, it generated an augmentation schedule and populated it. Now, what do you expect to see when the Augmentation Optimizer successfully runs? So let me show you some of the results that you are going to get. Going back to the slide. Okay. So when the Augmentation Optimizer runs successfully, you will see that there is a Show Results button under Augmentation Optimizer. It is going to become enabled. So this button here is going to become enabled, and you will be able to click it, and that is going to give you access to these images. So there are basically three output images from the Augmentation Optimizer. The first one will show you that all the scenarios that it has run. So in this particular case, it ran 59 different scenarios. And the one that it found to be most cost effective was the 7th one. And that is about 7% less expensive than the most expensive option that it evaluated. So you are actually getting 7% in saving by optimizing your augmentation strategy in this case. Then it also is going to give you that POI capacity, right? Because one of the goals here is you want to make sure that you get an augmentation schedule that maintains the capacity throughout the project life. So here it will show you that it is telling you that you are able to maintain 400 megawatt hour throughout the 20-year project life. And it is recommending in this case, year 3, you come back and add some capacity. Year 7, you come back and add some, again, more capacity. And then year 12, you add some additional capacity, right? And then the other image, second image, it will show you here is the degradation estimates for all these different phases. And you will notice something in these graphs is the blue one here is your initial build. That's the initial system that you put in. And then you have phase 1. That's the new system, augmented system that you added. The green one is the second augmented, and the red one is the third augmented. And the degradation, if you pay attention, you will see that the degradation curves are not the same. They vary because when you add more capacity, you actually are not stressing your initial system as much. So you're putting in less stress to that system. So the degradation rate of your initial system is going to slow down. So that kind of dynamics are captured through the Augmentation Optimizer. So we do not apply the same state of health estimation for all the different phases. It's derived based on the system capacity and the signal that is going to be executed. All right, so let's go back to our discussion. Okay, so that's how the Augmentation Optimizer works. After you are successfully running it, it is going to populate this augmentation schedule, and then you are all set to go ahead and click the run button. But before we click the run button, I also want to review some of the revenue option that is here under financial. So we covered the model in details. On a project level, you also need to make some decisions. So here under revenue, you can choose whether you want it to be a tolling agreement or a merchant market, right? So if it's a tolling agreement, you select which is your placed in service area, year, what is your contract term, you can input that. And then you can enable or disable some of the performance matrices depending upon what you have in your contract. So you can enable energy capacity LD, enable RTE LD. So you have to set your guaranteed RTE. So if you, after the simulation, if your project is underperforming, you will see the impact of that on revenue. And then also the availability. You have to set your availability target and what your assumed actual availability. Once you've done that, you basically can then go ahead and run it. Okay, so while it runs, it might take a few seconds to run. I'm just going to go ahead, let it run and go ahead, jump to the report. People who are following along, once it's finished running, you can click, the generate report is going to become enabled and you can click that. And let's go ahead and review the report here together. So once you finish running and generate the report, you're going to get a report like that. A big portion of the report was already covered in the first segment. I want to touch base on the one that we didn't cover in detail. So first, a big portion of the report here will help you to assess the design that you have done. So in this case, what in the screen is showing you that in blue that what was actually required in terms of power by your system. So the profile that you have inputted, right? Because remember, our design basis here is this profile that we have given. So the blue here is showing you at different locations on your system, what is the power requirement. And the green here is telling you that what you are able to achieve with the system that you have designed. So here we see we're completely meeting it. So we're good from a power sizing perspective. On the energy side, we can see that we are falling short a little bit on the discharge side. We're not 100%, we are around 97 to 98%. Now the question obviously becomes, why is that? So the radar chart gives you the summary, telling you that yes, you are falling short a little bit on the discharge side. And the donut chart here is exactly telling you why you are falling short, where it is telling we are falling short about 1.76% of the time because of hitting the minimum SOC limit. That means the signal that we are giving and the system that we have designed, that signal is not charging this system enough, or the system is having more losses than that signal assumed. So we are all draining our battery more and is not able to follow that signal fully. Then the next part is important for your efficiency. So here it's telling you that your 1 cycle per day efficiency is going to be around 85.48 round trip efficiency. And if you remember, the guaranteed efficiency we gave is around 88%. So for this case, my system is underperforming. So we'll see that what is going to be the impact of that on our revenue. Then it also gives you the breakdown of your auxiliaries. And that's the point I made very earlier, that auxiliary consumptions depends very much on your ambient temperature profile. So here you'll see in Texas, in summer, it's consuming a lot of auxiliaries because it's having to do a lot of cooling, but in other months, it's not having to do as much. So here it's a monthly breakdown of your auxiliaries. There are different components of your auxiliaries. So all these are broken down in very detail. And in the Excel raw data that you can also generate from the simulation will give you every time step auxiliary consumption. Then you go about looking into some of the characteristics that how you actually utilize the battery. So here it's telling you that obviously you can see throughput and cycles per day. This use case was the battery was used heavily in the winter, sometimes more than a cycle, and then summer as well. But on the shoulder months, it was not being utilized as much for the use case that we ran. So the usage is varying. It's not a constant 1 cycle per day. It's varying depending on the market scenario. And then it gives you this state of health estimation that is completely based on the location, based on the use case profile of your project. So it tells you state of health, capacity, DC, RT, POI. Everything is specific to your project, not based on generic assumptions. Then the most important check is this, right? Because our eventual goal is we want to get the most cost-effective solution, but it needs to meet our technical requirements. So here you'll see that in terms of capacity, we can see that the augmentation schedules that we got after executing them, the project is going to be able to meet 400 megawatt hour throughout the project life, and it's very optimally done here. Then the big portion of the discussion is around net present value of cost. In the first example, we covered it, so I'm going to skip that. On the Opex side, I want to highlight a couple of things here. So you will see that there are some certain jumps happening. Those are the year basically we had to do and come back and do augmentation. So augmentation is part of the Opex cost. And you can also see the different breakdown of your augmentation cost. The green one is your battery cost. This was an AC augmentation. So you had inverter cost as well. And the gray one is your augmentation, basically ancillary cost for your augmentation site works. Now on the revenue, this example, we did a fixed tolling agreement, right? So the revenue, that's why you see it constant, not changing. It's fixed constant on the revenue side. But what you'll notice here is that on the negative axis, there are some penalties happening. So we will see that RTE that I mentioned that we are falling short. You will see that RTE LDs is basically increasing with time, because with time, at year 0, our RTE is less than the 88%. And then with time, RTE is going even down, right? Because battery is aging, it is becoming less efficient. So the RTE difference starts to go. And because of that, you will take a hit. You have to pay for the LDs, and that will impact your net revenue on the project and impact your cash flow. Then you take that all this information and you put it all together into one graph, right? So this is the overall cash flow graph that you get. On the large red bar here on the negative side is your CapEx initially. Then you have your ITC. We're applying it at year 0. That's that blue bar. And the orange bar here is your depreciation. So you will see that up until year 5, you have your depreciation. Then you have your net revenue, operating revenue in green, and then your Opex is showing up on the negative axis in this yellow. So everything is packed up together, and the unlevered IRR that you accrue in this case is around 9.5%. And if you were to assume a discount rate of 5%, the project was going to break even at around year 13. Okay. So now that we have seen how to go about designing it and optimizing a design for one particular configuration, now we can go back to the slide and look at some iteration of it. So all this we have done for AC augmentation. Now, if we want to understand, okay, instead of doing AC augmentation, if we were going to do DC augmentation, how my results vary, right? So you can actually do that as well. And we also provided an example file that's called same file name, but underscore DC. You can go ahead and run that. But in that scenario, you will select the DC option under augmentation type, run the augmentation optimizer. Is going to give you an augmentation schedule based on DC. And once you look at the results, you will see that augmentation schedule is a little bit different for AC versus DC. Not a lot, but there are some difference based on the parameters that we have selected. So once we've done the augmentation AC and DC, we have some observations. So first observation that I wanted to highlight is you will see that there is degradation difference between AC and DC, even though shows minimal for this case, but there are, and then for different scenarios it can get bigger. But the more important thing to notice is compare this green and blue curves with this orange curve. And this orange curve is what we had of the initial systems degradation, right? And that's what is a typical practice here. You make an initial system SOH degradation, and you assume that's going to be the degradation even after augmentation. And that's actually not the case. You will see that as you are adding more battery capacity, so you'll see up until year 3, those all are same. But as you kept adding more new batteries through augmentation, the degradation of your initial system started to slow down. And that's an important factor to take into account. You'll see over the period of 20 years, it can be as large as, in this case, I think 6% or so. So that's very important nuance that often gets missed if we apply the same degradation curve for all augmentation phases. Second thing, we went over it as a result of the Augmentation Optimizer, so I'm not going to cover it any further here. The one that I want to cover is the comparison of the augmentation schedule, so AC versus DC. So in this case, both shows that both are having a first 3-year overbuild, but then the overbuild amount is different. So DC had more overbuild done at year 3, more augmentation done at year 3 than the AC. AC augmentations are happening at year 3, year 7, and year 12. And then DC augmentations are happening at year 3, year 8, and year 14. So we kept everything same, location same, use case same, equipment same, just varied the type of augmentation. And that is causing us the augmentation schedule to be different. We also covered this observation, the round trip efficiency, like we were discussing, our target is 88, and then our actual RTE was much less than that, and that cost us RTELD that we could see. Overall cost of ownership comparison, so we observed that the AC system was more expensive than the DC one. In this case, it was more driven by the cost of inverters, and around 1.2% difference in the cost overall NPV cost of the project between AC augmentation and DC augmentation. And then when you put it together, if you give the same revenue and cost assumptions on the IRR, DC one gives you 9.7% IRR versus the AC one, which we just ran around 9.5. So there is a gain of 0.2% switching from AC augmentation to DC augmentation. And also wanted to show you, of course, different market has different revenue streams depending on your contract structure. Your return is also going to be very impactful. That's very intuitive. But if you tie that for this example, tolling agreement, we got 9.5% for AC. For the merchant market, the revenues for ERCOT market is not doing that great. With the current market rates, doesn't look like it's going to be profitable on just based going by the merchant market. If you tag along some other contract strategy or other revenue stacks on top of it, then maybe you can make it work, but just going by merchant market makes it difficult to pencil out. And then, so that brings us to the end of, the parameter that can potentially impact, how impactful deployment strategies are, how impactful different contract types are to my return. Now, if you want to take this thought and expand it over markets, right? So let's say now I want to develop this same 100 megawatt, 400 megawatt hour battery and think of it from a developer portfolio perspective. You have the option to deploy that capital either in ERCOT or PJM or MISO, which is the best market for you to deploy that capital. So in this case, we try to design the same battery, 100 megawatt, 400 megawatt hour for these 6 different markets. And what we got is the overall NPV cost it came out to be the cheapest for ERCOT because ERCOT 1, the dispatch profile was not utilizing the battery as much compared to SPP. Looked like every day you are doing energy arbitrage and a full cycle and using the battery a lot. So that eventually caused SPP and NYISO, New York ISO, their cost to be on the higher side than ERCOT and others. So over the spectrum here, we end up getting around like 10% difference in cost. So then the next question obviously becomes, how does that impact our IRR? And how does we gain efficiency compared to the current practice? Because right now, everywhere you're going, you're just trying to buy a 1 cycle per day battery, right? You're not really taking the use case of the market into account when you're trying to purchase that battery. So what in this next graph here is, we have two approaches. One is that use case specific sizing, like what we just saw in our exercise today, where we are inputting a market specific signal, versus a generic sizing where you don't know, you're not actually inputting a market specific signal, rather just saying, I'm going to do a 1 cycle per day battery. So that's one. Generic sizing is the blue one, and then the use case specific sizing is the green one. And what you end up seeing there in almost all the markets, the generic sizing actually is giving you less IRR, because most of those markets, the battery are not actually doing 1 cycle a day. So you are actually buying a battery that you don't really need. You're expending more, and in that process, your cost is elevated, and then that's causing you to get less IRR. And compared to that, if you shift to use case specific sizing, you can get better cost assumption and performance assumptions or performance matrices that allows you to optimize your IRR. And in this case, for ERCOT, we could even see as much as 2% difference in IRR, especially in a market that is that competitive and where the revenue prices are going down. 2% is huge. So there is a lot of efficiency that can be gained by doing use case specific sizing.
Okay, 2 minutes left here. We appreciate everyone. Thank you for attending, and we'll catch you next time. Thank you, everyone.